Hi guys, hi there. In this video, I'm gonna talk about something really cool, super cool actually, and something which is easy to understand. I'm gonna talk about linear regression, okay? Linear regression. Consider, consider we have some data. We have some data. The number of hours a student studied and the score that is achieved by the student. That is achieved by the student. Okay. So, and hours. Usually, the more number of hours a student study, the score also gets increased, right? Score also get increased in most of the cases. There are some outliers. I don't consider them in this case. Okay, as the number of hours studied, score get increased. Score get increased. Here, linear means a line, right? A line. So what we are going to try to do is in linear regression is we are going to find out a line that best fit this data, that best fit this data. What is the advantage of that? What is the advantage of that? When we will get, when we'll get a new data, when we will get a new data, like say here X, we can predict the score that could be that could be achieved by studying this much of hours, X hours. The score could be predicting Y cap. Okay, that's basically linear regression. We are going to find out the best fit line to a data so that we can predict in future for the given data what will be the score. Like given how number of hours a student studied, what will be the score? Okay, but the in reality, the thing is that it need not be need not be um, exactly correct. The value we predicted and the actual value, say the value we predicted is y cap, but the actual score that is achieved by the student is this. This is the actual data. So we can see that there is some error. There is some error. This is the actual data and this is the predicted data, and we can see that this is the error here. So anyway, in linear regression, even if we find out the best fit line, there will be some error. What is meant by best fit line? Best fit line usually means that we are going to find out the line that have the least amount of error. Least amount of error. Let's now just dive into some mathematical terms, right? Okay, okay. Um, Here what we're gonna try to find is that we are gonna try to find the error in this line. Okay, a line can be find out like this, or even this. But the thing is that we want to find out the line that have the least error. That is what we are going to try to do here. First of all, we'll try to come up with an equation for the error. So we are going to find out mean squared error. Basically, we are going to take the average, that's meant by mean, and it'll come from the right side. Okay, we're going to find out the error here in this case the error is y minus y cap. Okay, we are going to square it. We are going to square it to remove the negative sign, as well as the penalty for increasing the error will be squared. Okay, and we're gonna take the summation for each of this data. we are gonna find the error, and we are going to take the sum of all those errors, and from I to M, consider we have M number of data, M data. Okay, we will find out the summation, and we are gonna take the mean of this error. This is basically mean square. In linear regression, what we are going to do is that we are going to find out the line which has the least amount of error. How we find out the equation of a line that have least amount of error is by using gradient descent. Gradient descent. Okay. Here we have already found out the error 1 by n. I'm I'm taking the number of data as n here, okay? 1 by n sigma I equal to 0 to n y I minus y cap squared, okay? Squared. Here y cap is equal to what? What? We are predicting the data, the score, by using the linear equation, right? Y is equal to mx plus c. So basically what we want to find out is the m and the c. Now I'm gonna plug this equation to this one. E equal to 1 by n sigma I equal to 0 to n yi minus, what is it? mxi plus c. Okay, what we are going to do is that we want the m and c that will be having the least amount of error. So I'm going to find out partial derivative of everything excluding m will be kept as constant. So there is a square also here, square also. I'm gonna apply chain rule here, sigma I equal to 0 to n. By applying chain rule, it will be these two x raised to, we are like taking this whole thing as one, and we are applying a differentiation here. X2 into, like, this two will come here, 2 into yi minus mxi plus c, and then take the inner part. We are applying chain rule here. We take the inner part and take the derivative. Here everything except m is constant, so this whole thing will be turning to 0, and only thing that is left is minus xi minus xi. It will be the same. It will be the same for dou e by dou. We are going to find out C also, right? So it will be the same for C, and except this X won't be here. X won't be here. Okay. Minus 1 by n sigma e equals 0 to n 2 into yi minus mxi plus c. This will be the equation for C. What basically the partial derivative will give is that to which direction we can increase the error. To, to which direction we can increase the error. To which direction in terms of m we can increase the error. If you want a visualization of that, please comment below. Okay. To which direction we can increase, uh, to which direction we should move in terms of m to increase the error. In our case, we want the opposite. So this will give the direction to which we can increase the error. But what we want is to reduce error. So what we'll do is, we do in gradient descent is that we'll find out the m by doing m minus L into dou E by dou M. We'll find out the gradient and we'll find out the partial derivative and we'll be minusing this because we want the opposite, right? We want the m value that will decrease the error. So we'll minus that uh, derivative, partial derivative in terms of L. L is called learning rate. Learning rate. We can increase the L basically to uh, to increase how fast the linear regression learn and comes to the most optimum M. Okay. Similarly, what we'll find C by C minus L into dou E by dou C. Okay, we'll try to find out the best fit line that minimizes this error. So how we are gonna do that? How we are gonna do that? We are gonna do that by finding the derivative, partial derivative of this m and c, and we'll find out the m and c with minimum error by minusing, by subtracting the m by learning rate into the partial derivative of m. Similarly for uh, partial derivative of c. By doing this repeatedly, we'll find out the m and c, basically the line equation that have the minimum error. This step is called gradient descent. As a whole, this is basically linear regression.